Picture this. Right now, at this very moment, there are galaxies racing away from you, faster than the speed of light. Not at the speed of light, faster. And here's the kicker, this doesn't break any laws of physics. In fact, Einstein himself would nod in agreement. I know what you're thinking. We've been told our entire lives that nothing can travel faster than light. It's the universe's ultimate speed limit, right? 299,792,458 meters per second. The cosmic speed limit sign that can never be broken. Teachers drilled it into us. Documentaries repeat it like gospel. It's one of the fundamental pillars of physics. But what if I told you that while light obeys this speed limit religiously, space itself is the universe's ultimate rule breaker? What if I told you that the very fabric of reality is expanding faster than light, has been since the Big Bang, and will continue to do so for the rest of time? And the most mind-bending part? This isn't some fringe theory or controversial hypothesis. This is observed, measured, documented fact. Right now, there are stars whose light will never, ever reach Earth. Not in a billion years. Not in a trillion years. Never. They're out there, shining brilliantly, but their light is fighting a losing battle against the expansion of space itself. The photons are racing toward us at maximum speed, yet they're actually getting further away from us with each passing second. It's like running on a treadmill that's accelerating faster than you can possibly run. Before we dive deep into this cosmic paradox that will fundamentally change how you see reality, do me a favor, hit that like button and subscribe, because we're about to embark on a journey that's going to break your brain in the best possible way. And drop a comment telling me which country you're watching from and what time it is where you are. I love seeing this global community of curious minds come together. Now, let's shatter everything you thought you knew about the universe. To understand how space breaks the ultimate speed limit, we first need to understand what that speed limit actually is and why it exists. Because here's the thing, when Einstein published his special theory of relativity in 1905, he wasn't just making up random rules. He discovered something profound about the nature of reality itself. The speed of light isn't arbitrary. It's not like someone decided, okay, light should go this fast and no faster. The speed of light is actually the speed of causality itself. It's the speed at which cause and effect propagate through the universe. It's the speed of information, the speed at which anything can influence anything else. Think of it like this. Imagine you're standing in a perfectly still pond. You throw a rock in, creating ripples. Those ripples can only spread so fast. That's the speed of causality in the pond. Nothing in that pond can send a signal faster than those ripples. The speed of light is the universe's version of those ripples. It's the fastest. That cause and effect can propagate through the fabric of spacetime. Albert Einstein figured this out through pure thought experiments. He imagined what would happen if you could ride alongside a beam of light. What would you see? If you could match light's speed, wouldn't the light wave appear stationary to you, like a frozen wave? But Maxwell's equations of electromagnetism didn't allow for stationary light waves. They only worked for light, moving at one specific speed. This paradox led Einstein to a shocking conclusion. The speed of light must be constant for all observers, regardless of how fast they're moving. Let that sink in for a moment. If you're standing still and measure the speed of a light beam, you'll get 299,792,458 meters per second. If you're on a spaceship traveling at half the speed of light and measure that same light beam, you'll still get 299,792,458 meters per second. Not the speed of light minus your speed, the exact same number. This isn't an approximation or a trick. It's one of the most precisely verified facts in all of physics. But how is that even possible? How can something have the same speed for everyone, no matter how fast they're moving? The answer is mind-blowing. Time and space themselves must be flexible. They must stretch and compress. to ensure that light always has the same speed for every observer. This is where things get weird. When you move faster, time literally slows down for you. Not metaphorically, not apparently actually slows down. Your watch ticks slower. Your heartbeat slows. Your aging process decreases. This isn't science fiction. It's measured reality. Atomic clocks on GPS satellites have to be constantly adjusted because they're moving fast enough that time runs differently for them than for us on Earth. Without these adjustments accounting for relativistic time dilation, your GPS would be off by kilometers within a day. And it's not just time-space contracts, too. If you could somehow accelerate to near light speed and look at the stars ahead of you, they would appear bunched together. The distances between them would literally shrink from your perspective. Meanwhile, an observer watching you would see you flattened in the direction of your motion, like you'd been squished in a cosmic vice. In 1971, physicists Joseph Haffel and Richard Keating conducted one of the most elegant experiments in physics. They took 4 atomic clocks, among the most precise timekeeping devices ever created, and flew them around the world on commercial airliners. When they compared these traveling clocks to identical clocks that stayed on the ground, they found exactly what Einstein predicted. The flying clocks had aged slightly less. We're talking billionths of a second, but the effect was real and measurable. This is the foundation we need to understand. Nothing with mass can reach the speed of light because as you accelerate closer to light speed, several things happen. Your mass effectively increases, requiring more and more energy to accelerate further. Time slows down for you. Distances contract. To actually reach the speed of light would require infinite energy, and you'd experience time stopping completely. The universe has built-in mechanisms that prevent you from breaking this cosmic speed limit. Only massless particles, like photons, can travel at light speed, and they don't experience time at all. From a photon's perspective, if it could have one, it's emitted and absorbed in the same instant, regardless of whether it travels for a nanosecond or a billion years from our perspective. So the speed of light is absolute. It's the universe's ultimate speed limit. It's written into the very fabric of reality. Nothing can break it. Except space itself doesn't have to follow this rule. And here's why that's about to blow your mind. Now here's where everything you just learned gets turned on its head. The speed limit, this cosmic law that nothing can exceed, only applies to objects moving through space. But what about space itself? Imagine you're on a stretchy rubber sheet and someone starts pulling the edges of the sheet in all directions. You're not moving across the sheet itself is expanding, carrying you along with it. You haven't broken any speed limit by moving across the rubber. The rubber itself is expanding. This is what's happening with space, except in 3 dimensions and on a cosmic scale that defies imagination. In 1929, an astronomer named Edwin Hubble made one of the most important discoveries in human history. Working at the Mount Wilson Observatory in California, using the most powerful telescope of his era, Hubble noticed something strange about distant galaxies. Their light was shifted toward the red end of the spectrum, what we call redshift. And the farther away a galaxy was, the more its light was redshifted. This redshift wasn't because the galaxies were glowing red. It was because they were moving away from us, and the Doppler effect was stretching their light waves. Just like how an ambulance siren sounds lower pitched as it drives away from you, light waves get shifted toward the red when their source is moving away. But here's what made Hubble's discovery so revolutionary. He found a pattern. The farther away a galaxy was, the faster it was receding. Galaxies twice as far away were moving away twice as fast. 3 times as far, 3 times as fast. This relationship, now called Hubble's law, could mean only one thing. The universe itself is expanding. Not expanding into anything. Not expanding from a central point. Every point in space is moving away from every other point, like dots on the surface of an inflating balloon. If you're on any galaxy in the universe looking out, every other galaxy appears to be moving away from you. You're not at the center. Everyone is at the center from their own perspective. Now, here's where it gets insane. If space is expanding and distant galaxies are being carried along by that expansion, how fast can they be moving away from us? Is there a limit? The answer is no. There is no limit. The expansion rate of space is described by something called the Hubble constant. Current measurements put it at about 70 kilometers per second per megaparsec. Don't worry about the units. Here's what it means. For every 3.26 million light-years of distance between us and a galaxy, that galaxy is receding about 70 kilometers per second faster. Let's do the math. A galaxy 3.26 million light-years away is receding at 70 kilometers per second. A galaxy 326 million light-years away is receding at 7,000 kilometers per second. A galaxy 4.28 billion light-years away is receding at about the speed of light, 299,792 kilometers per second. And here's the kicker. Any galaxy farther than that is receding faster than light. Not approaching light speed, faster. Right now, there are galaxies racing away from us at twice the speed of light, 5 times the speed of light, 10 times. And this doesn't violate relativity because they're not moving through space faster than light. Space itself is expanding, carrying them along. Think of it like this. Imagine 2 ants on opposite ends of a stretching rubber band. The ants can only walk 1 centimeter per second. That's their speed limit, and they can't exceed it. But if the rubber band itself is stretching at 10 centimeters per second, the ants are getting farther apart at 10 centimeters per second, even though neither ant is walking faster than 1 centimeter per second. The ants aren't breaking their speed limit. The medium they're on is expanding. This is the universe. We're the ants. Space is the rubber band, and it's stretching faster than light can travel across it. But wait, it gets even more mind-bending. Because the expansion of space isn't even constant. It's accelerating. In 1998, 2 teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, made a discovery so shocking that it won them the Nobel Prize in Physics. They were studying distant supernovae, trying to measure how the universe's expansion has changed over time. Everyone expected to find that the expansion was slowing down. Gravity, after all, should be pulling everything back together, acting as a brake on the expansion. Instead, they found the opposite. The expansion of the universe is speeding up. Let me repeat that because it's absolutely insane. The universe isn't just expanding. It isn't even expanding at a constant rate. It's expanding faster and faster with each passing moment. There's some kind of energy, we call it dark energy. Though dark just means we don't know what it is that's pushing space apart with ever-increasing strength. About 68% of all the energy in the universe is this mysterious dark energy, driving the acceleration of cosmic expansion. Another 27% is dark matter we can't see, but we know is there from its gravitational effects. That means all the normal matter every star, planet, galaxy, and atom we've ever observed. Everything we're made of, everything we've ever touched or seen, makes up less than 5% of the universe. We're living in a universe where 95% of everything is completely unknown to us. We can measure its effects, but we have no idea what it actually is. It's like discovering that your house is 95% invisible rooms you didn't know existed. Because of dark energy, the expansion of space is accelerating. Galaxies that are currently receding from us at, say, twice the speed of light will eventually be receding at 3 times the speed of light, then 4 times, then 10 times. And here's the truly cosmic tragedy. There's a boundary around us, called the cosmic event horizon, beyond which galaxies are receding so fast that their light will never reach us. Never. Think about that. There are stars out there, shining brilliantly, whose light is headed in our direction at maximum speed, the speed of light, but the space between us and them is expanding so fast that the light is actually getting farther away from us with each passing second. It's like trying to swim against a current that's stronger than your maximum swimming speed. You're giving it everything you've got, but you're still being swept backward. Right now, our observable universe is about 93 billion light years in diameter. But there's more universe beyond that. We just can't see it because the light from those regions hasn't had time to reach us yet, or can't reach us because space is expanding too fast. The actual size of the full universe could be infinite. We literally don't know because we're trapped in our observable bubble, unable to see beyond the cosmic horizon. And that bubble is actually shrinking in a sense. Not in size, but in content. Galaxies that we can see now will eventually disappear from view as they cross our cosmic event horizon and begin receding faster than light. In trillions of years, observers in our galaxy will look out into space and see almost nothing. Just the galaxies in our local group, gravitationally bound to us. Everything else will have raced away beyond the horizon. Future astronomers will look at an empty cosmos and have no evidence that the Big Bang ever happened, no evidence that the universe is expanding, no evidence of anything beyond their local cluster. We live in a special time when we can still see the broader universe, when we can still detect the cosmic microwave background radiation from the Big Bang, when we can still observe the expansion. In the deep future, that privilege will be lost. But here's what I want you to think about. Space doesn't care about light speed limit. Space isn't made of stuff moving through space. Space is the stuff. It's the stage itself, not the actors on it. And the stage can expand as fast as it wants because there's nothing moving through anything else. There's no violation of causality, no information traveling faster than light. It's just the growth of space itself. Now let's talk about what this means for the structure of spacetime. Because this is where Einstein's general theory of relativity comes in, and where things get really trippy. Special relativity, which Einstein published in 1905, dealt with objects moving at constant speeds in the absence of gravity. It's the theory that gave us EMC, time dilation and length contraction. But it had a problem. It couldn't account for acceleration or gravity. So Einstein spent 10 years developing a more comprehensive theory. In 1915, he published General Relativity, and it fundamentally changed our understanding of gravity and the nature of space and time. Here's the revolutionary idea. Gravity isn't a force. Read that again. Gravity isn't a force pulling you toward Earth. Instead, mass and energy warp the fabric of spacetime itself, and objects move along the curves of that warped spacetime. Think of it like this. Imagine spacetime as a trampoline. If you place a bowling ball in the center, it creates a depression. Now roll a marble across the trampoline. It won't travel in a straight line. It'll curve around the depression created by the bowling ball. The marble isn't being pulled by the bowling ball. It's following the curvature of the trampoline. That's gravity. Earth isn't pulling you down. Earth's mass warps spacetime around it, and you're simply following the straightest possible path through that curved spacetime. You're in free fall, but the ground keeps getting in the way. This might sound like philosophical hairsplitting, but it has real, measurable consequences. One of the most famous confirmations of general relativity came in 1919, when astronomer Arthur Eddington measured the positions of stars during a solar eclipse. Einstein had predicted that the sun's mass would warp spacetime enough to bend the light from distant stars passing near it, making the stars appear slightly displaced from their true positions. Eddington's measurements matched Einstein's predictions perfectly. The headline in the London Times the next day read, "Revolution in Science, New Theory of the Universe. Newtonian Ideas Overthrown." Overnight, Einstein became the most famous scientist in the world. But here's where it connects to our expanding universe. If mass warps spacetime, what about the expansion of space itself? What's causing that? In Einstein's field equations of general relativity, he actually included a term called the cosmological constant, a kind of energy inherent to empty space itself, but he later called it his biggest blunder, because he added it only to make the universe static, which he believed it should be. When Hubble discovered the expansion, Einstein removed the cosmological constant. The field equations of general relativity don't just allow for space to expand, they describe how it expands. And crucially, they place no speed limit on that expansion, because space isn't moving through spacetime. Space is spacetime. It's not an object moving through a medium. It's the medium itself growing. Here's an analogy. Imagine the universe as a loaf of raisin bread dough. The raisins are galaxies, and the dough is space. As the bread bakes and the dough expands, the raisins get farther apart. But no raisin is moving through the dough faster than any other. The dough itself is expanding, carrying the raisins with it. And there's no limit to how fast the dough can expand because it's not violating any speed limit for objects moving through space. Now, the expansion of space has another wild implication. It means space can be created. In fact, it's being created right now, all around you, at every point in the universe. Between you and the screen you're looking at, new space is being created. The effect is infinitesimally small at these distances, roughly 1 atom's width per year, across the distance of our solar system. But it's happening. On cosmic scales, this is dramatic. Every second, roughly 3 new soccer fields worth of space is created between the Milky Way and any distant galaxy. And that's conservative, based on nearby galaxies. For very distant galaxies, the amount of new space being created is mind-boggling. This raises a fascinating question. If space is being created, where is it coming from? What's it made of? These questions don't really make sense in the framework of general relativity, because space isn't made of anything, it's just the geometric relationships between events. When space expands, those geometric relationships change. More space doesn't mean more stuff. It just means the distances between things get larger. But quantum mechanics might have a different story to tell. In quantum mechanics, empty space isn't actually empty. This is one of the weirdest, most counterintuitive discoveries in all of physics, but it's been verified experimentally hundreds of times. According to quantum field theory, what we call empty space or vacuum is actually seething with activity. Virtual particles are constantly popping into and out of existence, borrowing energy from the vacuum for tiny fractions of a second before annihilating and paying it back. This isn't speculation. We can measure this. In 1948, Dutch physicist Hendrik Casimir predicted that if you place 2 metal plates very close together in a vacuum, the quantum fluctuations between the plates would be slightly different from the fluctuations outside the plates, creating a tiny attractive force, pushing the plates together. This Casimir effect has been measured with incredible precision. Empty space has real, measurable energy. So here's the mind-bending part. If the vacuum of space has energy, and energy can warp spacetime according to general relativity, then the vacuum itself can drive cosmic expansion. This vacuum energy might be dark energy. When you calculate how much vacuum energy there should be, based on quantum field theory, you get a number. When you measure how much dark energy there actually is in the universe, you get a different number. And these numbers don't just disagree. They disagree by a factor of 10,120. That's 1 followed by 120 zeros. It's the worst prediction in the history of physics. This is called the cosmological constant problem, and it's one of the deepest mysteries in modern physics. Why is the vacuum energy so much smaller than quantum mechanics predicts it should be? We have no idea. But the fact remains, there is vacuum energy, and it is driving the expansion of space. Now let's connect this back to our question. Why can space expand faster than light? Because space isn't bound by the same rules as matter and energy, moving through space. The speed of light limit exists to prevent paradoxes. If you could send information faster than light, you could theoretically send messages backward in time, creating grandfather paradoxes and causality violations. But the expansion of space doesn't transmit information. If a galaxy is receding from you faster than light due to cosmic expansion, you can't send a signal to it, and it can't send a signal to you. There's no violation of causality because there's no causal connection. You're not in the same causal patch of the universe anymore. Think of it like this. Imagine two ships sailing away from each other on an ocean that's constantly growing. The ocean is expanding so fast that the distance between the ships increases faster than the ships could sail toward each other, even at maximum speed. The ships themselves haven't exceeded their maximum sailing speed. The ocean between them has just grown too large. And if the ocean is expanding fast enough, the ships can't even send radio signals to each other, because by the time a signal crosses the expanding ocean, the ships are even farther apart. That's us and distant galaxies. The cosmic ocean between us is expanding faster than light can cross it. But here's something that will really bake your brain. The expansion of space means that the universe doesn't have a center. When Hubble discovered that all galaxies are moving away from us, people naturally asked, does that mean we're at the center of the universe? The answer is no, and also yes, and also every galaxy is at the center. Remember the balloon analogy? If you draw dots on a balloon and inflate it, every dot moves away from every other dot. If you're an ant standing on any dot, all the other dots appear to be moving away from you. You're at the center of the expansion from your perspective, but so is everyone else from their perspective. There's no preferred center point. The universe is expanding, but it's not expanding into anything. There's no outside. There's no edge. Or if there is an edge, it's beyond our observable universe, beyond our cosmic horizon, forever out of reach. The universe could be infinite, and an infinite universe that's expanding is still infinite, just with more space between things. This is hard to visualize, because our brains didn't evolve to understand cosmic scale space-time geometry. We evolved to throw spears and avoid predators, not to comprehend infinite expanding space. Let's bring this down to something more personal and explore what the expansion of space means for the fate of everything we know. The acceleration of cosmic expansion has profound implications for the future of the universe. And when I say profound, I mean potentially lonely, cold, and dark beyond anything you can imagine. Right now, we're in what cosmologists call the stelliferous era, the age of stars. Stars are being born, galaxies are active, and the universe is relatively bright and happening. But this won't last forever. Saul Perlmutter, who won the Nobel Prize for discovering the accelerating expansion, described it like this. Imagine you're at a cosmic party, and the room is getting bigger and bigger, faster and faster. Eventually, you're so far from other party-goers that you can't even see them anymore, can't communicate with them, can't reach them no matter how fast you run. You're alone in an ever-expanding room. That's the future of the universe. The acceleration of expansion means that galaxy clusters will become increasingly isolated. The Milky Way, Andromeda, and the few dozen galaxies in our local group are gravitationally bound together, will likely merge into one enormous elliptical galaxy in about 4.5 billion years. But everything beyond our local group will eventually recede beyond our cosmic event horizon. In about 150 billion years, an observer in our merged galaxy will look out into space and see almost nothing. Just the stars of their own galaxy. The cosmic microwave background radiation will have been stretched into undetectability. There will be no evidence of the Big Bang, no evidence that the universe was once smaller and denser, no evidence of cosmic expansion. The entire story of cosmology will be erased from the observable universe. Future scientists, if they exist, will be unable to discover what we've discovered. They'll look at the evidence available to them and conclude they live in a static, isolated galaxy surrounded by empty space. They'll be wrong, but they'll have no way to know it. We live in a privileged time. A time when the evidence of our cosmic origins is still visible. A time when we can still see the universe's expansion, still detect the afterglow of the Big Bang, still observe distant galaxies, and piece together the history of everything. But wait, it gets even more intense. Eventually, we're talking trillions upon trillions of years from now, the last stars will burn out. New stars won't form because the gas and dust will have been used up or dispersed. The universe will enter the degenerate era, lit only by the fading glow of white dwarfs, neutron stars, and black holes. Then, in 1,040 years or so, even white dwarfs will have cooled to black dwarfs. In 10,100 years, protons themselves might decay, causing all remaining matter to slowly disintegrate into radiation. And eventually, in 10,100 to 10,106 years, even black holes will evaporate through Hawking radiation. The universe will end up as a cold, dark, almost empty void with a temperature just barely above absolute zero. Just occasional photons and fundamental particles separated by vast, ever-increasing distances. Infinite space with virtually nothing in it. This is called the Big Freeze or heat death, the ultimate fate of an accelerating universe. Unless dark energy changes, unless it decays or transforms into something else, unless the laws of physics have surprises we haven't discovered yet. But based on what we know now, this is where we're headed. Now, I don't want you to feel depressed about this, because we're talking about timescales that are incomprehensibly vast. The universe is 13.8 billion years old. We're talking about events trillions of years in the future. Humanity has existed for maybe 300,000 years. Civilization for maybe 10,000. We have so much time, so many possibilities ahead of us. But here's what I want you to take from this. The universe is strange and beautiful and temporary. The fact that we exist at all, in this brief cosmic moment, when stars are shining and galaxies are visible, and the evidence of our origins is still detectable, that's remarkable. You are a pattern of atoms that became conscious, living in a universe that's expanding faster than light, in a moment when that expansion can still be observed and understood. You're made of stardust that has assembled itself into something that can contemplate the cosmos. That's not just poetic language, that's literal truth. Now let's talk about the observational evidence for all this cosmic weirdness, because this isn't just theoretical speculation. We've actually measured it. The cosmic microwave background radiation, the CMB, is one of the most important pieces of evidence we have for the Big Bang and the expansion of space. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, the CMB is the afterglow of the Big Bang itself, the oldest light in the universe. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque. Photons couldn't travel far before being scattered by free electrons. But once atoms formed, the universe became transparent and light could travel freely. That light has been traveling through space ever since, but the expansion of space has stretched its wavelengths from visible light to microwaves. What was once searing radiation is now a faint microwave glow with a temperature of 2.725 Kelvin, just a few degrees above absolute zero. The CMB surrounds us in every direction. It's the most distant thing we can see, the edge of our observable universe. And it's incredibly uniform, the same temperature in every direction, to within 1 part in 100,000. This uniformity is actually evidence for cosmic inflation, a period in the first fraction of a second after the Big Bang, when space expanded exponentially fast, much faster than the speed of light. Cosmic inflation is space expansion on steroids. In less than a trillionth of a trillionth of a trillionth of a second, space expanded by a factor of at least 1026. a region smaller than a proton was stretched to the size of a galaxy or larger. This sounds absurd, and it is absurd, but it explains several puzzles about the universe, including why the CMB is so uniform. Alan Guth proposed cosmic inflation in 1980, and Andre Linde further developed the theory. The idea is that a special field, the inflaton field, drove this exponential expansion. When inflation ended, the energy of the inflaton field converted into matter and radiation, creating everything we see today. During inflation, space was expanding so fast that regions of space were separating faster than light by enormous factors. And here's the crucial point. This wasn't a problem. It didn't violate relativity. It was just space doing its thing, expanding without limit. We've also measured the expansion rate of the universe in multiple ways, and they all confirm that space is expanding and accelerating. By observing Type Ia supernova stellar explosions that have a known luminosity, we can measure how far away they are and how fast they're receding. By studying the patterns in the CMB, we can determine the expansion rate in the early universe. By measuring the distribution of galaxies, we can trace cosmic expansion over billions of years. All of these measurements agree. Space is expanding, and the expansion is accelerating. But here's a problem that's emerged in recent years, and it's a big one. Different measurement methods give slightly different values for the Hubble constant, the rate of cosmic expansion. This is called the Hubble tension, and it's one of the most exciting mysteries in cosmology right now. Measurements based on the CMB give a Hubble constant of about 67 kilometers per second per megaparsec. Measurements based on nearby supernova and Cepheid variable stars give about 73. That might not sound like a big difference, but it's statistically significant. It's a real discrepancy, and we don't know why. Maybe our measurements are wrong. Maybe there's some systematic error we haven't accounted for. Or maybe, and this is the exciting possibility, there's new physics we don't understand. Maybe dark energy isn't constant. Maybe the expansion rate changes over time in ways we haven't predicted. Maybe there's something fundamentally wrong with our models of the universe. Scientists love mysteries like this because they point the way toward new discoveries. Every time we found a discrepancy between theory and observation, it's led to breakthroughs. Let's explore some of the more exotic implications of faster-than-light expansion. Because once you accept that space can expand without limit, some truly bizarre scenarios become possible. One of the most mind-bending is the concept of eternal inflation. Proposed by Andre Linde and others, eternal inflation suggests, while inflation ended in our region of space, it's still ongoing in other regions. Space is infinitely larger than our observable universe, and in some regions, inflation never stops. Picture it like a pot of boiling water. In our region, a bubble formed and inflation stopped, creating our universe with its galaxies and stars. But beyond our bubble, inflation is still happening, and other bubbles are constantly forming, each one potentially becoming its own universe with its own laws of physics, its own constants of nature. This is the multiverse hypothesis in its most radical form. Not only could there be other universes, but there could be infinitely many of them, constantly being created, each one isolated from the others by the faster-than-light expansion of space. We could never detect these other universes, never travel to them, never communicate with them. They're forever beyond our cosmic horizon. Some of these universes might have different physical constants, different strengths of gravity, different masses of fundamental particles, different numbers of dimensions. Most of them would be sterile, unable to form complex structures like atoms, molecules, or life. We happen to exist in a universe where the constants are just right for complexity and consciousness. Is this science or philosophy? That's a matter of debate. We can't test it directly. But it's a natural consequence of our best theories of cosmic inflation combined with quantum mechanics. And it fits with the observation that our universe seems fine-tuned for life, not because it was designed, but because we're in one of the rare bubbles where the constants happen to be right. Another implication: cosmic horizons are real and fundamental. There are parts of the universe that we can never, ever reach or observe, no matter how advanced our technology becomes. Not because the technology doesn't exist, but because the laws of physics forbid it. Imagine you build a spaceship that can travel at 99.99% the speed of light. You point it toward a galaxy that's currently receding at twice the speed of light due to cosmic expansion. What happens? You fly toward it as fast as physically possible, yet it gets farther away from you. You're like a runner on a treadmill that's moving backward faster than you can run forward. Even if you could travel at exactly the speed of light, which you can't if you have mass, you still couldn't reach galaxies beyond a certain distance, because space between you and them is expanding faster than you can cross it. This means there are absolute, fundamental limits to how much of the universe we can explore. Currently, we can, in principle, reach any galaxy within about 18 billion light years. Beyond that, they're receding too fast, and that boundary is shrinking. Every day, galaxies cross that threshold and become forever unreachable. Future civilizations, if they want to explore the universe, have a ticking clock. Not because they'll run out of fuel or time, but because the universe itself is pulling away from them faster than they can chase it. This might sound depressing, but I find it strangely beautiful. The universe is vast, almost beyond comprehension, yet still finite in what we can observe and reach. We're in a cosmic island, and that island is slowly shrinking as space expands around us. Now let's talk about wormholes, warp drives, and whether the expansion of space gives us any loopholes in the cosmic speed limit, because this is where science fact meets science fiction in fascinating ways. Einstein's general relativity allows for some truly bizarre solutions. Wormholes, shortcuts through space-time, connecting distant points, are mathematically possible in general relativity. You could, in theory, step through a wormhole and emerge light years away, effectively traveling faster than light without ever exceeding the speed of light locally. The catch? Every known wormhole solution requires exotic matter with negative energy density to keep the wormhole open. And we've never found any matter or energy with genuinely negative energy density in amounts needed for a traversable wormhole. Quantum effects can produce tiny negative energy densities in limited regions, like the Casimir effect, but nowhere near enough to create a macroscopic wormhole. Then there's the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. The idea is to contract space in front of a spaceship and expand it behind, creating a warp bubble that carries the ship along. The ship itself wouldn't be moving faster than light relative to the space immediately around it, but the bubble could move faster than light. It's like surfing. The surfer isn't moving faster than the wave, but the wave carries the surfer faster than they could swim. In this case, space itself is the wave. The problem? The Alcubierre drive also requires exotic matter with negative energy, and the energy requirements are astronomical, possibly more energy than exists in the entire observable universe. Some more recent analyses have reduced the energy requirements, but it's still wildly beyond anything we could produce. But here's the thing. These aren't prohibited by the laws of physics. They're just engineering challenges so monumental that they might as well be impossible. General relativity doesn't forbid them. It just makes them incredibly difficult. And this connects back to our main theme. Space is weird and flexible in ways that matter and energy are not. You can't accelerate a particle faster than light, but you might be able to manipulate space-time itself in exotic ways that effectively achieve faster than light travel without violating causality. Whether any civilization, no matter how advanced, could actually do this remains an open question. But the fact that it's not ruled out by fundamental physics is fascinating. Some physicists have speculated about advanced civilizations potentially manipulating dark energy, or even creating localized regions where the expansion of space is reversed or controlled. If dark energy is a property of space itself, and if we could understand it well enough, Maybe we could engineer spacetime on large scales. This is wildly speculative, but it's fun to think about. A civilization that could control the expansion of space could create warp bubbles, stabilize wormholes, or even create pocket universes. They'd be engineering reality itself. We're nowhere near this level of technology. We don't even fully understand what dark energy is, let alone how to manipulate it. But the universe has already shown us that space is more than just an empty stage. It's a dynamic, flexible entity that can expand, contract, and warp. And if space can naturally expand faster than light, then maybe, just maybe, there are ways to harness that for our benefit. Or maybe not. Maybe the speed of light limit is truly absolute for information and causal influence, even if space itself can cheat. Either way, the universe is telling us something profound. The rules are more complex and interesting than we initially thought. Let's zoom back to something you can relate to directly. What does all of this mean for your understanding of reality? How does the expansion of space change the way you should think about the universe and your place in it? First, it means the universe is not static. This seems obvious now, but it's a profound shift from how humans thought for thousands of years. We assumed the cosmos was eternal and unchanging. The stars were fixed points, the heavens were permanent. We now know that everything is in motion, everything is evolving, and everything is temporary. The universe had a beginning. It's changing now. It will have an end, at least in any form we'd recognize. This temporariness extends to everything. The atoms in your body were forged in stars that exploded billions of years ago. Those atoms will persist long after you're gone, but eventually, even they might decay. On long enough timescales, nothing is permanent. But here's the flip side. You exist at all. Against incredible odds, in a vast and mostly empty universe, atoms assemble themselves into a pattern complex enough to be self-aware. You're a way for the universe to know itself, as Carl Sagan put it. And you exist at a special time, a time when the universe is still young enough, still dense enough, still slow enough in its expansion that we can see our cosmic origins. Future civilizations won't have that privilege. Second, it means the universe is far, far larger than we can ever observe. Our observable universe, everything we can possibly see, is just a tiny bubble in what might be an infinite cosmos. Most of reality is forever beyond our reach, separated from us by the expansion of space. This should be humbling. We're not just small in space. We're small in observability. We're limited not just by our technology, but by the fundamental structure of spacetime itself. Yet somehow, despite these limitations, we've figured out how the universe works. We've measured the expansion rate. We've traced cosmic history back to fractions of a second after the Big Bang. We've determined the age, size, and composition of the observable universe. We're tiny, temporary patterns of atoms in an incomprehensibly vast cosmos, yet we've comprehended the cosmos. That's remarkable. Third, it means the universe doesn't have to make intuitive sense. Space expanding faster than light violates our common sense, but common sense evolved to help us survive on the African savanna, not to understand cosmic scale space-time geometry. The universe doesn't care about our intuitions. It operates according to mathematical laws that often produce results that seem paradoxical or impossible. Particles can be in two places at once. Time passes at different rates for different observers. Space itself can expand without limit. Our job isn't to make the universe conform to our expectations. Our job is to observe, measure, and build models that accurately predict what we see, even if those models seem bizarre. This is why science is so powerful. It's a systematic method for overcoming our cognitive biases and limitations. It forces us to accept reality as it is, not as we wish it to be. Fourth, and maybe most importantly, you're part of this story. You're not separate from the expanding universe, observing it from the outside. You're in it, made of it, subject to its laws. Every atom in your body is participating in the cosmic expansion, albeit on scales so small it's unmeasurable. The space between electrons in your atoms is governed by the same physics that governs the space between galaxies. You're connected to the cosmos in the most literal sense. You're not in the universe. You are the universe, a localized portion of it that's become conscious and is now contemplating the whole. And here's the thing, knowing all this doesn't diminish life. It enriches it. Understanding that you're made of stardust, that you exist in an expanding cosmos, that the atoms in your left hand came from different stars than the atoms in your right hand. This adds depth and meaning. You're not just living a life. You're participating in the universe's journey of self-discovery. Now, let's address some of the common questions and misconceptions about cosmic expansion, because this topic is rife with confusion, even among people who've studied it. Question 1. If space is expanding, why aren't we expanding? Why aren't atoms getting bigger? Why aren't you getting stretched apart? The answer is that the expansion of space only affects things that aren't held together by forces stronger than the expansion itself. Atoms are held together by the electromagnetic force, which is vastly stronger than the expansion of space on atomic scales. Your body is held together by chemical bonds, which are electromagnetic. The Earth is held together by gravity. The solar system is held together by gravity. The Milky Way galaxy is held together by gravity. Only on scales larger than galaxy clusters does the expansion of space overcome the forces holding things together. Galaxy clusters are the largest gravitationally bound structures in the universe. Beyond that, on scales of hundreds of millions of light years, expansion dominates. So you're not expanding. The Earth isn't expanding. The solar system isn't expanding. The Milky Way isn't expanding. But the space between galaxy clusters is expanding, and that expansion is accelerating. Think of it like dots drawn on a rubber sheet. If you glue some dots together, they stay together as the sheet stretches. Only dots that aren't glued, that aren't bound by forces, get pulled apart by the expansion. Question 2. What is space expanding into? If space is getting bigger, there must be something outside of it, right? This question assumes space is embedded in some larger space, but that's not how it works. Space itself is all there is. It's not expanding into anything because there's no outside for it to expand into. This is really hard to visualize because our brains think of space as a container, and containers have insides and outsides. But space isn't a container. It's the totality of all locations. When space expands, new locations come into existence between existing locations. That's all. The balloon analogy helps here. Imagine the surface of a balloon as a 2D universe. As the balloon inflates, the surface expands. But the surface isn't expanding into the 3D space around it from the perspective of 2D beings living on the surface. For them, the surface is all there is. It's getting larger, but not into anything. Our 3D space is similar. It's expanding, but not into a 4D hyperspace or anything like that. It's just expanding. More space is coming into existence. Question 3. Didn't the Big Bang happen everywhere at once? How can we look back and see it in a specific direction? This is a subtle point. The Big Bang did happen everywhere. Every point in space was part of the Big Bang. But we can only see the Big Bang from points in space where light from that event is just now reaching us. The cosmic microwave background we see is light from the Big Bang that's been traveling for 13.8 billion years to reach us. It's coming from a sphere around us at a distance of 13.8 billion light years. In terms of light travel time, though the actual current distance is about 46 billion light years due to expansion. We're seeing the Big Bang not as a point or direction, but as a shell around us in all directions, the surface of our observable universe. We're at the center of our observable universe, but so is everyone else in their observable universe. It's all relative. If you could instantly teleport to a galaxy 10 billion light years away, you'd see a different cosmic microwave background shell around you, representing a different region of the Big Bang. Question 4. If the universe is expanding and accelerating, Will it eventually tear apart atoms and even subatomic particles in a big rip? This is a possibility, but only if dark energy increases in density over time. If dark energy is constant, a true cosmological constant, then the expansion accelerates, but bound structures stay bound. The universe ends in a big freeze, not a big rip. But if dark energy is something called phantom energy, which increases in density as the universe expands, then yes, eventually the expansion becomes so violent that it overcomes all forces. First, galaxy clusters get torn apart, then galaxies, then solar systems, then planets, then molecules, then atoms, then even atomic nuclei and fundamental particles. This big rip scenario would end the universe in a finite time, maybe 22 billion years from now, depending on the parameters. Everything would be shredded down to the smallest constituents, and then even those would be torn apart. Current evidence suggests dark energy is constant, not increasing, so the big freeze is more likely. But we're still figuring this out. Question 5. Could the expansion of space ever reverse? Could we end up in a big crunch instead? Based on current observations, no. The expansion is accelerating, and there's no sign of it slowing down. For a big crunch to occur, dark energy would need to disappear or become attractive instead of repulsive, and there's no evidence that's happening or will happen. But cosmology is full of surprises. Before 1998, most scientists assumed the expansion was slowing down. We were wrong. Maybe we're wrong about other things too. The honest answer is we don't know the ultimate fate of the universe with certainty. We can only extrapolate based on what we observe now. And right now, it looks like endless expansion leading to a cold, dark, empty future. Let's talk about some of the cutting-edge research and unsolved mysteries in cosmology, because this field is evolving rapidly, and there's so much we still don't understand. The Hubble tension I mentioned earlier is one of the hottest topics right now. The fact that different measurement methods give different expansion rates could mean we're on the verge of a major discovery. Some possible explanations. Maybe dark energy isn't constant. Maybe it was different in the early universe than it is now. If the properties of dark energy change over time, it could explain why early universe measurements from the CMB and late universe measurements from supernova disagree. Maybe there's additional physics we're missing. Perhaps there are types of particles or fields we haven't discovered yet that affect cosmic expansion. Some theories propose early dark energy, a component that was important in the early universe, but not now. Or maybe our standard cosmological model, called lambda CDM, is wrong or incomplete. Lambda CDM assumes cold dark matter, CDM, and a cosmological constant, lambda. It's been remarkably successful at explaining observations, but maybe it's missing something fundamental. Researchers like Adam Rees are pushing to resolve this tension with more precise measurements. The James Webb Space Telescope, launched in 2021, is helping by observing distant supernova and galaxies with unprecedented clarity. We should know more in the coming years. Another mystery: what exactly is dark energy? We've given it a name, but that doesn't mean we understand it. Is it truly a cosmological constant energy inherent to space itself? Is it a new field, like the inflaton field that drove cosmic inflation? Is it something even weirder, like a modification to general relativity on cosmic scales? Different theories make different predictions. Quintessence models suggest dark energy is a dynamic field that changes over time. Phantom energy models suggest it increases in density. Modified gravity theories suggest gravity works differently on very large scales. And what we interpret as dark energy is actually just our misunderstanding of gravity. We're trying to distinguish between these possibilities by measuring how dark energy has affected cosmic expansion throughout history. By looking at distant supernova, the large-scale structure of galaxies, and the CMB, we can trace how the expansion rate has changed over billions of years. Then there's dark matter, which is a different mystery but equally profound. We know dark matter exists because we can see its gravitational effects on galaxies and galaxy clusters. Galaxies rotate too fast to be held together by the gravity of visible matter alone. Galaxy clusters have more mass than we can account for with stars and gas. But we don't know what dark matter is made of. Leading candidates include WIMPs, weakly interacting massive particles, axions, and primordial black holes. Despite decades of experiments, we haven't directly detected dark matter particles yet. And here's a fun twist. Dark matter doesn't participate in the expansion of space in the same way that radiation does. Dark matter is matter. It clumps together under gravity. But dark energy causes expansion to accelerate. They're opposite effects, and the balance between them determines the fate of the universe. Early on, matter, both normal and dark, dominated, and gravity slowed the expansion. As the universe expanded, matter density decreased because the same amount of matter occupied a larger volume. But if dark energy is constant, its density stays the same, even as space expands. So eventually, dark energy took over, and expansion started accelerating. This transition happened relatively recently in cosmic history, about 5 to 6 billion years ago. Before that, expansion was decelerating. After that, accelerating. We happen to live in the era when dark energy is becoming dominant. Another unsolved mystery. Why is the universe so flat? When cosmologists measure the curvature of space, they find it's almost exactly zero. The universe is geometrically flat on large scales. This is weird because flatness is unstable. If the early universe had even slightly more or less density than the critical density, it would have rapidly become very curved. Cosmic inflation solves this by expanding space so dramatically that any initial curvature gets stretched flat, like how the surface of a balloon appears flat if you inflate it to an enormous size. But this raises the question, what caused inflation? And why did it end? We have theories, but no definitive answers. There's also the horizon problem. Why is the CMB so uniform in all directions? Regions of the CMB that are on opposite sides of the sky were never in causal contact. They're too far apart for light to have traveled between them in the age of the universe. So how did they end up at exactly the same temperature? Again, inflation solves this. If those regions were much closer together before inflation and came into thermal equilibrium, then inflation expanded them to opposite sides of our observable universe while preserving that equilibrium. But it's a remarkable fine-tuning. All of these mysteries point to the fact that despite our incredible progress in understanding the universe, we're still missing big pieces of the puzzle. The universe is still surprising us, still revealing new mysteries as we peel back each layer. And that's exciting. It means there's still so much to discover. As we head toward the end of this journey, I want to bring everything back to a fundamental level and explore what all of this means philosophically and personally. The fact that space can expand faster than light tells us something profound about the nature of reality. The universe is not bound by the rules we're familiar with in everyday life. Intuition is a poor guide to cosmic truth. For thousands of years, humans believed the universe was small, static, and centered on Earth. We thought the stars were fixed points on a celestial sphere. We thought the laws of physics on Earth were different from the laws in the heavens. Every single one of those assumptions was wrong. Each step has been humbling. We're not at the center of the universe. We're not even in a typical part of the universe. We're in a small, dense region, while most of the universe is empty space. We're made of atoms that represent less than 5% of the universe's content. The rest is dark matter and dark energy that we can't see and don't fully understand. And yet, despite all this, we've figured it out. We've measured the expansion of space. We've traced the universe's history back 13.8 billion years. We've determined the cosmic inventory, how much normal matter, and dark energy there is. We've tested our theories with incredible precision. Humanity has existed for a blink of cosmic time on a tiny planet orbiting an average star in a typical galaxy, yet we've comprehended the universe. That's astonishing. It means consciousness, intelligence, and curiosity are powerful. They allow matter to understand the universe it's part of. Now, here's where it gets personal. You are part of this cosmic story, not as a spectator, but as a participant. The atoms in your body were created in stars. Your hydrogen atoms, the ones in your water, in your DNA, were created in the Big Bang itself. They're 13.8 billion years old. Your heavier atoms, carbon, nitrogen, oxygen, iron, were forged in stars that lived and died before the sun existed. You are literally stardust that has become conscious. And the space you occupy, the space between the atoms in your body, is governed by the same physics that governs intergalactic space. The electromagnetic force holding your atoms together is the same force that prevents atoms from expanding with the universe. You're subject to the same laws as everything else. You're not separate from the cosmos. You're a piece of it, a local configuration of atoms and energy that's complex enough to be self-aware. And here's the most mind-blowing part. The universe created you, not through conscious design, but through natural processes, stars forming, supernova exploding, planets coalescing, chemistry becoming complex enough for life, evolution sculpting that life into beings capable of thought. The universe gave rise to you, and now you're contemplating the universe. You're a way for the cosmos to know itself, to understand its own nature, to wonder at its own existence. Think about that. The same processes that create galaxies, that drive the expansion of space, that forge atoms in stellar cores, those processes also created you. You might feel small and insignificant in comparison to the vastness of the cosmos. And in some ways, you are. You're tiny in space, brief in time, limited in what you can observe and reach. But you're also incredibly significant. You're rare. The universe is mostly empty space and radiation. Complex structures like you are the exception, not the rule. And you're capable of understanding most of the universe is mindless matter following physical laws without awareness or comprehension. You're one of the universe's ways of knowing itself. That's not small or insignificant. That's profound. And the knowledge you've gained today, the understanding that space can expand faster than light, that the universe had a beginning and will have an end, that we're living in a special cosmic moment, that knowledge connects you to something larger than yourself. You're part of a species that has decoded the cosmos. You're part of a lineage of consciousness that stretches back through evolutionary history, a lineage that has produced beings capable of measuring the expansion rate of the universe, of detecting the afterglow of the Big Bang, of predicting the ultimate fate of everything. That's not meaningless. That's beautiful and awe-inspiring. So here we are, at the end of our journey through the expanding cosmos. Let's bring it all together and leave you with some final thoughts. We started with a paradox. Light has a speed limit, but space doesn't. Nothing can move through space faster than light, but space itself can expand as fast as it wants. This isn't a loophole or a trick. It's a fundamental feature of how reality works. Space isn't a thing moving through space. Space is the framework, the stage, the geometric relationships between events. When it expands, those relationships change. Distances increase, galaxies move apart, and there's no speed limit on this process, because nothing is actually moving through anything else. We explored Einstein's relativity, which gave us the mathematical tools to understand spacetime as a flexible, dynamic entity. We learned about Hubble's discovery of cosmic expansion, which revealed that the universe had a beginning and is evolving. We examined the acceleration of expansion, driven by mysterious dark energy that makes up 68% of the universe's energy content. We discussed the implications. The Big Freeze as the ultimate fate of the universe, a cosmic event horizon beyond which we can never reach, the possibility of a multiverse where other bubble universes exist beyond our cosmic horizon. We addressed misconceptions and explored cutting-edge mysteries like the Hubble tension, the nature of dark energy, and the question of what came before the Big Bang. And finally, we connected it all back to you, to the fact that you're made of stardust, living in an expanding universe, part of the cosmos itself. Now, what should you take from all this? First, question your assumptions. The universe is under no obligation to make sense to you. What seems impossible might just be counterintuitive. What seems obvious might be wrong. Stay curious, stay humble, and always be willing to update your understanding when new evidence emerges. Second, appreciate the privilege of existence. You're alive at a time when the universe is knowable, when the evidence of cosmic expansion and the Big Bang is still visible. You're made of atoms that have been recycled through multiple generations of stars. You're a pattern that has become conscious and is now contemplating the universe. That's miraculous, not in a supernatural sense, but in the sense of being wonderful and rare. Third, embrace the unknown. We don't understand dark energy. We don't know what dark matter is. We don't know if the multiverse is real. We don't know the ultimate fate of the universe with certainty. And that's okay. That's exciting. It means there's still mystery, still discovery ahead. Science isn't a collection of facts. It's a process of discovery. And the process is ongoing. Future generations will know things we can only guess at. They'll solve mysteries we haven't even thought of yet. And you're part of that journey. Fourth, recognize that knowledge changes everything. Before you watched this video, you probably thought the speed of light was an absolute limit. Now you know better. You understand that space itself can expand without limit, that the universe is accelerating toward a cold, dark future, that we're living in a special cosmic moment. This knowledge doesn't make you more powerful in a physical sense. You can't stop the expansion of space or reverse entropy, but it changes how you see yourself and your place in the cosmos. You're no longer just a person living a life. You're a conscious being in an expanding universe, capable of understanding that universe, capable of comprehending the forces that created you and the processes that will outlast you. That understanding is empowering. It connects you to something larger than yourself. It gives you perspective. When you're stressed about daily concerns, remember, you're on a planet orbiting a star in a galaxy that's part of an accelerating expansion that will eventually carry most of the universe beyond our reach. Your problems are real and valid, but they're also temporary and small in the grand scheme. When you feel insignificant, remember, you're made of atoms forged in stars, arranged in a pattern complex enough to contemplate the cosmos. You're rare, you're conscious, and you're capable of understanding. That's significant. When you feel isolated, remember, you're connected to everything. The same physics governs you and distant galaxies. The same processes created you and stars. You're part of the universe, not separate from it. And when you wonder about the meaning of life in a universe that will end in heat death trillions of years from now, remember, meaning isn't given by cosmic processes. It's created by conscious beings like you. You get to decide what matters, what's meaningful, how to spend your brief time as a pattern of consciousness in an expanding cosmos. The universe doesn't care about you. It's indifferent. But that indifference is liberating. It means you're free to care about what you want, to create your own meaning, to live according to your own values. And here's my final thought. Share this knowledge. Talk about it. Think about it. Let it change how you see the world. You now understand something profound about reality. You know that space can expand faster than light, that the universe is accelerating toward an empty future, that we're living in a privileged cosmic moment when the evidence of our origins is still visible. Don't keep that to yourself. Spread the wonder. Inspire others. Encourage curiosity and scientific literacy. Because in a universe that's racing toward heat death, in a cosmic moment that will eventually pass, the most meaningful thing we can do is understand, appreciate, and share the incredible journey we're all on together. You're a pattern of stardust that became conscious in an expanding universe. You've now gained insight into that universe, how it works, where it came from, where it's going. Use that knowledge. Let it inspire you. Let it humble you. Let it connect you to the cosmos and to the billions of other conscious beings sharing this journey with you. Thank you for spending these last 3.5 hours with me, exploring one of the most profound questions in cosmology. If this expanded your mind, hit that like button, subscribe for more deep dives into the nature of reality, and share this with someone who loves thinking about the big questions. Drop a comment telling me what blew your mind the most. Was it the cosmic event horizon? The fact that galaxies are receding faster than light? The idea that space itself is expanding without limit? The privilege of living in a time when we can still see the Big Bang's afterglow? I read every comment, and I love hearing how these ideas affect you. Until next time, keep looking up, keep questioning, and keep marveling at this strange, beautiful, expanding cosmos we call home. The universe is vast, ancient, and mostly empty. But for this brief cosmic moment, you're here, aware, and understanding. That's not just remarkable, it's miraculous in the truest sense of the word. Thank you for being part of this journey. Now go forth and see the universe with new eyes.